BiPC&MPC.com.
Okay, students, in this lecture, we are going to complete chemical equilibrium from very basics to advanced level. And at the end of this lecture, there will be some very important topic like Lee-Chatler principle and some tricks and direct shortcut methods also I will tell. So try to be attentive and make a proper notes from the beginning to the end of the class. Okay. So maintaining proper notes is very must because your revision and your selection will be completely depends on how you maintain the proper notes. Okay. So let's start with the one by one. And first topic is about the equilibrium. Okay. So in the equilibrium and chemical kinetics, these are the two chapters which are interrelated to each other. And in the chemical kinetics also, and the states of matter, surface chemistry. These are the some chapters where the importance of graphs are very, very important. Okay. And there what is given on the x-axis, what is given on the y-axis also plays a vital role. Okay. So if you change one variable and appear to be very same, slight variable, slight variation in the variable on the x and y axis will entirely change the graph. Okay. So first of all, what is equilibrium? Basic definition of the chapter. Equilibrium is not only for chemistry. Okay. It is for everything. But in chemistry, we will explain in the terms of the concentration. Okay. So equilibrium is the state at which concentration of reactant and product, concentration of reactant and product do not change with time. Okay. So initially to before attaining the equilibrium, there will be change in concentration. But once equilibrium is attained, the concentration is going to be the same. Concentration is going to remain constant. Okay. As long as you do not disturb by any stress. What is stress and how you will apply, that will come to know at the end of this lecture. Until unless you don't apply the stress and once equilibrium is attained, the concentrations are going to be constant with time. Okay. So that state of that reaction, is called as a equilibrium. Equilibrium definition, I think it is clear now. Now very important objective, theoretical objectives are coming on the basis of characteristics. So people are not able to understand from the language given in the books and not able to convert them into objectives. So I will elaborately explain how the questions are framed and how you have to tackle them. Okay. So following are important equilibrium state. Now this is the graph drawn by taking concentration on x-axis, time on y-axis. Okay. So here initially once we time is 0, that means we will have only reactant. Okay. So that time product quantity will be 0. As we proceed the time, then slowly product will keep on forming. Okay. Product will keep on forming and reactant will keep on consuming. So you will find a decremental in the concentration of reactant. You will find a incremental in the concentration of product at certain point of time. So suppose this is the point of time. After that, this concentration is going to be constant. This concentration also going to be constant. Okay. So this is the time where we say that equilibrium is attained. Before this, there is no equilibrium. Okay. So this is how the graphical explanation. Make sure that this is concentration and on the x-axis it is time. Okay. Then only this graph will be applicable. Now let's see the next. Characteristics are very important, especially direct theory based questions. Okay. So understanding between the lines of NCERT is very must. Okay. That is what I am going to do it now. So the equilibrium state can be recognized by constancy of certain measurable properties. every time we will not be able to measure the concentration alone. There are certain direct hints which will give you that equilibrium is attained. Like pressure is becoming constant. You keep a manometer with that closed container. As soon as pressure is start rising and start increasing or start decreasing, that means reaction is started. Once keep on increases or keep on decreases at certain level, it remain constant. So that means equilibrium is attained. Our density is constant, our color is the best method, our pressure is the best method if possible. They are not possible every now and then. Otherwise, there is the final method will be concentration. Okay. So as soon as these things are constant, then we will understand that equilibrium is attained. So by changing these conditions of system, we can control the extent to which reaction proceeds. What is this meaning? That we, in the latter slides we will try to understand. Okay, extent of reaction. What is extent of reaction? That I will explain in the latter slides. Okay, then equilibrium state can only be achieved in closed vessel. Okay, so but it is not necessary for every time. It is closed vessel only when one of the reactant, most of the reactant, all of the reactant or products are in gaseous state. Okay, so but if process is carried out in open vessel, equilibrium is cannot be attained in the open vessel. Okay, because in the open vessel what happens, products or reactants will be escaping, so they may not react back to give the reactant, therefore equilibrium state may not be achieved. Okay, this is specially applicable for what, when gaseous product or gaseous reactant are present, so the reverse process may not takes place. Okay, first thing is measurable properties like density, pressure, color, concentration will become constant. Second thing, if any of the reactant or products are in gaseous state, you have to carry out in the closed vessel. Okay, and reaction equilibrium is reversible in nature. Frankly speaking, equilibrium exists only in the reversible reactions only. Okay, so this is about the few characteristics. Some more characteristics we are going to learn now. Okay, so these characteristics you will understand only when you go through the related questions. So practicing the questions immediately after the lecture is will be the best effective way. Okay. Now let us see the next point. Fourth point about the characteristic. Equilibrium is also dynamic in nature. Dynamic means appearing to be very calm. Appearing to be very calm internally, lot of process will be going out. Okay, so when you see from outside, you will feel that equilibrium is stopped, a reaction is stopped, but at the microscopic level, okay, dynamic means moving. At microscopic level, system is in moving or motion. Okay, so that is what dynamic in nature. Understood? Like people say he is a dynamic personality, but appears does not. Okay, dynamic personality means lot of process, lot of thinking will be doing, but it will not come out on his face. Understood? Same is with the equilibrium. Okay, equilibrium appear to be stopped, a reaction is stopped, but internally both reaction will be taking place, forward reaction and backward reaction. But why we don't understand? Because both are occurring at the same speed. Okay, because both reactions are taking place at the same speed, net speed will be zero. Okay, so that is what called as a dynamic in nature. Okay, so this is the basic condition for equilibrium. At equilibrium, rate of forward reaction. Forward reaction means reactant converting into product is forward reaction. And backward reaction will be for product react giving back reactants. See here, what is the difference in the previous graph we have taken here? Concentration. Okay. Now we have taken rate of reaction. What is the difference between those two graphs? So they are remaining constant, but not essentially same. Okay. So after this point of time, they are remaining constant, but they are not same. But once I take the rate of reaction on X and Y axis, sorry, y-axis, then they are not only constant, they are equal also. Okay, keep two things in mind. At equilibrium, concentration of all reactant and product become constant, may or may not be equal. Second point, at equilibrium, rate of reaction of forward and backward both become constant and equal. Okay, so that is the minute difference you will find when you change the parameter on the y-axis. Okay, so this is about the equilibrium in terms of the graph with respect to rate of reactions. Okay, now let us see some more. Okay, now equilibrium is not only applicable for chemically changing in reactant and product. Sometimes reactant and product can be chemically same. Okay, chemically both reactant product can be same. Like here also H2O and here also H2O. Okay, chemically same, but what is changing here? It is ice, that is solid, and here it is liquid. So the reactions where the equilibrium where reactant chemical formula, product chemical formula both are same, but still equilibrium is attained, then it is called as a physical equilibria. Okay, if the chemical formula of the reactant and products are different, then they are called as a chemical equilibria. So there are two types of equilibria: physical equilibria and chemical equilibria. So these type of equilibria, solid and liquid equilibria, is attained at the freezing point. Is attained at what? Freezing point. And at the freezing point, rate of freezing. At the freezing point, rate of freezing is equal to rate of melting. Okay, rate of melting. So then same way, liquid to vapor. This will takes place at the boiling point. This will takes place at the boiling point, and at the boiling point rate of vaporization is equal to rate of melting. Okay, rate of sorry, condensation. Okay, rate of condensation. Rate of condensation. Okay, condensation means converting from gas to liquid. Same way, solid to gas. Solid to gas. Okay, this is only possible when they are sublimate. When they are sublimate, okay, then only it is possible and it will takes place. This is more important. I will put a star mark so that you can get idea what to study during your revision. Okay, here what is the important point? This is important, will takes place below melting point. Okay, this will takes place where? Below melting point. Okay, so this will takes place at freezing point, this will takes place at boiling point. Okay, and this will takes place below melting point. Okay, and here rate of freezing equal to rate of melting. Okay, and freezing means liquid to solid, solid to liquid will be melting, and liquid to vapor is vaporization, vapor to liquid is condensation. So solid to gas, it is applicable only when sublimate is there and it takes place below melting point. Rate of sublimation is equal to rate of condensation. Okay, now here solid and saturated solution. Okay, let us take an example. This requires example. NaCl solid. Okay, here also it will be NaCl. Okay, but it will be aqueous here. Chemical formula of the solution and solute are same. Okay, so that time you keep on and it will takes place where? Saturated solution. Like I told you, this will takes place in freezing point, this will takes place in boiling point, this will takes place in the saturated solution. Where it will takes place? Saturated solution. Okay, and in gas vapor, saturated solution of gas in liquid. Okay, so this is also saturated solution, and the pressure is called as a saturation pressure. Only thing here solute is solid here and here solute is gas. Rest all are same. These are the five types of physical equilibrium. These are the five types of physical equilibrium. Okay. Okay, next characteristics of chemical equilibrium. Okay, so it is a dynamic equilibrium. Already I told you at this stage reaction takes place in both direction, but no net change. Okay, then at equilibrium reaction proceeds both sides equally. At equilibrium, both concentration of product and reactant do not change with time. The state of equilibrium is not affected by presence of a catalyst. Very, very important. It only helps in attaining equilibrium where if we use the positive catalyst in less time, if we use the negative catalyst in more time. Okay. Then change in pressure, temperature or concentration favors the reaction, thus shifts the equilibrium in one direction. So this is what Lee Chattel principle that we are going to discuss in the later slides. Okay. So these are some key points of the characteristics of chemical equilibrium. Okay. Now next slide, law of mass action. Okay. So this you will find in the chemical kinetics, but used in the chemical equilibrium. Okay. It was given by Goldberg and Wack. So at a given temperature, what is the statement? At a given temperature, the product of concentration of product, each raised corresponding to the stoichiometric coefficient balanced chemical equation divided by the product of concentration of reactant raised to the corresponding is called as a constant value. That means let us take a reaction, simple reaction, A moles of A and B moles of B reversible with C moles of C and D moles of D. Okay. So here stoichiometric coefficient, this will be a constant when product of this is product means multiplication. Okay, product of concentration of product, okay, and concentration of reactant divided by concentration of reactant. Okay, concentration of reactant will be a constant. This is applicable for equilibrium state only. This is applicable for equilibrium state only. Okay. Now let's see the next slide. Okay. So according to this rate of chemical reaction, according to law of mass action, rate of chemical reaction is directly proportional to concentration of each reactant. Therefore, proportionality can be replaced with constant and k into a to the power of 1, b to the power of 1. So for the starting case, I am taking unitary stoichiometric. Unitary means these powers are how much? 1. Okay. So here also 1, here also 1. So rate of forward reaction, by using this rate of forward reaction, this is the forward reaction, this is the backward reaction. Okay. So rate of forward reaction is equal to Kf into a to the power of 1 and b to the power of 1. Okay. Where Kf is called as a rate constant, specific rate of reaction for the forward reaction. For the what? Forward reaction. Okay. So let's see the next slide. In the next step, what we will do, we will apply it for the backward reaction. So once you apply for the backward reaction, RB directly proportional to backward reaction. For the backward reaction, C and D will be the reactant and A and B will be the product. So RB will be equal to KB into C to the power of 1 and D to the power of 1. Okay. Where KB is a rate constant of backward reaction. KB is what? Rate constant of backward reaction. Okay. So at rate of reaction, actually if it occurs at the different net rate of reaction will be rate of forward reaction. This is very useful, not in this chapter, in the chemical equilibrium. Okay. So net rate of reaction will be equal to rate of forward reaction minus rate of backward reaction. So, but at equilibrium, what we assumed, both are same. Okay. Therefore, the difference must be zero. So, Kf upon Kb is equal to simplified C to the power of C into D, A into B. So, constant by constant, that is going to give you a new constant called as K equilibrium. What it is called as? K equilibrium. Okay. So this is for unitary concentration terms of the coefficients. Okay, but if they are non-unitary, that means some other moles are taken. Okay, so this is the condition when some other moles are taken, N1, N2, M1, M2. Okay, so in that condition, what you will do? Same thing we will do, but only thing, this type of coefficient will come into the exponents. Okay, so if they are unitary, then you need not to write them. But if they are non-unitary, then you have to write them in the coefficient, where square bracket means they are concentration. Okay, so let us take the next slide. Next, people think that there are only two types of equilibrium constants, Kc and Kp, but there are two more exist. Okay, that's why in the beginning only I told you we will start from the basic without missing a single topic from the basic. We will reach the all relevant information. Okay, Kc already I told you. Kc is the concentration, equilibrium constant in terms of the concentration. Okay, Kp is equilibrium constant in terms of the partial pressure. There are certain conditions existing. Some reactants are in aqueous solution, some reactants are in gases, some products are in aqueous solution, some products are in the gases. Okay, let me take one example. A is in aqueous, okay, and B is in gas, but it is in equilibrium with the C, which is in aqueous solution, and D, it is in gas. In that condition, this will be very handy. Okay, KPC. So for that KPC will be, KPC is equal to, for whichever substances are in aqueous state or solution state, we will take the concentration into B is in gaseous state. That time what we will take? We will take the partial pressure of B divided by C aqueous, concentration of C, into D gases, so partial pressure of D. Okay. So this is called as a P into C or PC. That means this they got a freedom to stay in the aqueous solution also, stay in the gases also. But it is restricted for the gases, this is restricted for the aqueous solution. Now let's see about the equilibrium constant in terms of the mole fraction. Okay. So in terms of what? Mole fraction. So Kx means mole fraction. Here for the same reaction, mole fraction of A in, sorry, oh, I have written this wrong. Product upon reactants. Very, very silly mistake. These type of mistakes you should not commit. Okay, so C, concentration of C into partial pressure of D divided by concentration of A into partial pressure of B. Okay, now here mole fraction of C, okay, into mole fraction of D divided by mole fraction of A into mole fraction of B. So the difference between these two, is it understood? Okay. So PC is used when some are in the gaseous state, some are in the aqueous state. And this universal best method is mole fraction. But due to the complication issues during the solution, this is less used. Most favorite and most of the examination, I say most of the. So, but in tough examinations like AIMS and advanced, they will be focusing on the complicated things only. Okay. So I don't want you to be in the most of the. Okay. I want you to be in the exceptional cases. Okay. So that is what the difference in the most of the and exceptional cases. Okay. So all equilibrium constant, now I think it is clear. Now characteristics of equilibrium constant. When I taught this in the before lecture, they said, sir, already you have taught this, sir. Okay. Okay, characteristics of equilibrium constant. So don't think that already we have studied. That we have studied of the characteristics of equilibrium. Now we are going to study about the equilibrium constant. Okay. So for the expression of equilibrium constant, K is applicable only when, you cannot use every now and then, only when they attained equilibrium. How you will understand that equilibrium is attained? That their values do not change with time. Okay. Next, the value of equilibrium constant is independent of initial concentration of reactant and product. You take any amount of reactant, any amount of product. Once temperature is fixed, then equilibrium constant is going to be fixed. Okay. Next, equilibrium constant has one unique value of a particular reaction represented by balanced equation at a given temperature. So K formula will be same when temperature is same and representation is same when representation is same. Okay. So these are the few characteristics, and very important characteristics is yet to come. So then this type of questions are very mostly asked in the state level examinations like MSET, KSET, MHT, CET, Haryana CET, Bihar CET, like that. State level examination, these are very important. Okay. But for advanced examination, for you wanted to get in the aims, these are obsolete. But these are indirectly asked. There will be some compilation of the new questions. Okay. Concept will be same. So the equilibrium constant for a reverse reaction is equal to inverse of the equilibrium constant of the forward reaction. Okay. Suppose in this direction means this is formation of HI. This is Kp. Here it is dissociation of HI. The Kp for the dissociation will be reciprocal of Kp for the reciprocal of the Kp for the formation. This is formation of HI. This is dissociation of HI. So when equation is reversed, equilibrium constant will be inversed. Equilibrium constant will be inversed. Is that understood? So this is very important. Direct questions are very rare. This will be mixed with, combined with some other concept. Okay. That how it is done, that we will do in the challenging questions. Okay. Our previous questions. Okay. So next, equilibrium constant K for a reaction related to the equilibrium constant corresponding to whose equation is obtained by multiplying or dividing equation. Okay. So this is a simple equation. Now we can say this is studied in the two directions. We can say total equation is divided by 2. Total equation is divided by 2 R. Divided by 2 R. Okay, so when this reaction, we can say this as a divided by 2 or multiplied by 1 by 2. Multiplied by what? 1 by 2. Understood? So whether it is divided by 2 or divided by n, then power will be 1 by n. Multiplied by n, power will be n. Okay, so like we can say this as a kp to the power of 1 by 2. Okay, so it is divided by 2 also 1 by 2, are multiplied by 1 by 2 also to kp to the power of 1 by 2. Okay. So when equilibrium equation is multiplied by some number, so that number will go to power. Understood? So that is what the fifth characteristics of the equilibrium constant. Fifth characteristics of the equilibrium constant. Okay. So I think all of you understanding. Let's go for the next. Multiple steps. There is a concept of two types of reactions are nowadays in the very frequently they are asking what are those multiple equilibria. Okay, what is that? Multiple equilibria and simultaneous equilibria. So that also I am going to cover. Don't think that in very short span of time, if it is teaching, so a lot of topics will be missing. Everything is planned and made the slides so that not a single topic must be missing. Okay. So multiple equilibria we are going to discuss, and simultaneous equilibria also we are going to discuss. But if you wanted questions, already those questions are discussed, solved and uploaded. Okay. So multiple steps. If the reaction takes place in multiple equilibria steps, so A is giving C and D, but problem is that C is further participating in equilibrium to give E, and problem is that D is reacting with the previous uh, E is reacting with the previous product D to form B. Okay. So when you add all of them, ultimately what you are getting, overall reaction of A to B. For this equilibria, this is a multiple equilibria. Then equilibrium constant of multiple equilibria will be product of all the equilibria, provided when they are added. Okay. Two things you remember: when two equations are added, okay, equilibria constant get will be multiplied. Understood? When two equilibria are when two equilibria are Okay, two equilibria, when they are added, you will multiply. When they are subtracted, sometimes we have to subtract also. We have studied in the thermodynamics Hess law. So that time they will be divided. Okay, subtracted will be divided, added will be multiplied. When two equilibrium equations are subtracted, they suppose this and this are subtracted, then it will be Kp1 by Kp2. If these two equations are added, Kp1 into Kp2. Okay. So this is what the reactions taking place in multiple equilibria and their equilibrium constant calculation. Okay. So let's see the next slide. Okay. Factors. Most of the people thinks that factors which do not influence equilibrium constant. Okay. So if I increase the concentration, see what the people answers during question session. Suppose if C and D, let us take to the power of 2. When concentration of A is made twice, when concentration of A is made twice, then equilibrium constant Kc becomes. Okay, this was a previous question in the Kerala CET. Okay, so what they have done, they have given two times. Okay, so first option itself they have given 4 times. Understood? So if you increase the concentration of A 4 times or 2 times, there will be manipulation in the concentration of B, C, and D such that Kc will remain constant. Understood? So, but according to this formula, it will not reflect. Okay. So, sometimes going according to the formula is not correct. Understood? This is one live example. Even though you increase the concentration of A 2 times, the Kc will remain constant. Okay. That is what the sentence and its related question and mistake done by the previous students. Okay. Then pressure and volume. You change pressure, you change volume. Initially it may be disturbed, but after that it will come back to the equilibrium state. Okay. Presence of catalyst and addition of inert gas at constant pressure and volume. At constant pressure and volume. Okay. Suppose here A concentration is made 2 times, then B concentration will decrease by 4 times, or C concentration and D concentration will also increase 2 times. Like that, they will manipulate each other so that increased concentration will not affect the concentration of Kc or value of Kc. Okay. So these are the factors on which Kc is independent. Kc is independent. Okay. On temperature, it will depend, Karthik. Okay. So question is final answer. Okay. So final answer is Kc is constant whether you change concentration of A, concentration of B, concentration of C or D. Okay. And here these are the factors which do not influence equilibrium constant value. Karthik, your answer is understood now. Okay. Now I will ask you question. What are the factors on which equilibrium constant changes? Equilibrium constant changes. Okay, when people ask about the what factor influence the equilibrium constant, 90% of the students knows that only temperature. But surprisingly, these many factors on which equilibrium constant depends. Okay, so temperature is famous, but to make yourself famous you should know the unfamous factors also. Okay, so mode of representation of chemical reaction. Suppose if I represent a equilibrium between a plus b gives c plus d. Okay, then if it is k, okay, the same equilibrium we can represent as a c plus d gives a plus b. So that time equilibrium constant is changed for this reaction, but equilibrium is changing. Okay, equilibrium is same. Okay, in that container you will find same quantity of a, b, c and d. So mode of representation will change the equilibrium constant value. Next, stoichiometry. Just now I told you if I multiply this with some number, then equilibrium constant will also change, and temperature. Okay, I too agree that temperature is important, but I don't agree that these are not important. Okay, so let's see the how the temperature variation will be there. Okay, so one of our previous scientists have derived some equation about the temperature. Okay, now, first one, what I told you just here. So here decomposition is Kc1, for formation it will be 1 by Kc1. Okay. Now next stoichiometry of reaction. If for this reaction it is Kc1, when it is multiplied by 1 by 9, sorry 1 by 2, then it will be to the power of 1 by 2. Okay. Like that there will be change. Next temperature. Okay. So as I told you, one of the scientists derived a equation for us for the comfortability, but nowadays they are giving the questions on the application part, understanding the formula. Okay, so those people who believe in by hearting the formula will be trapped over here. Okay, what is the topic? How they are going to ask that I will tell you in the next slide. Okay, this is called as a Van 't Hoff equation. So basic thing you should remember is Van 't Hoff equation gives the relation between dash and dash. It gives a relation between dash and dash. What should be the answer? Gives a relation between temperature and equilibrium constant. Okay. And normally students thinks that equilibrium constant will increase with increase in temperature. No. Okay. Sometimes it may decrease, sometimes it may increase. So that is what people are now framing the question. Okay. So this is the formula you have to write 2 to 3 times, and you have to very make sure when there is a positive, this is T1 and T2. Okay. When there is negative, T2 and T1. There was a question by changing these values, this minus was. Which of the following Van 't Hoff equation is correctly represented? So wherever traps are there in the previous question, going through the PYQ, will give you the reality test of your preparation. Sometimes you yourself may feel that my preparation is topmost, but when you attend the PYQs, you may not score the good marks because these type of traps will be there. Okay, so attempt the PYQ previous year question and make the traps into the flat. Okay, so that you should not be in the traps. Understood? So let us go for the next slide, which will give you the correct framing of the question. Okay. So what was the question and how you will answer, that we are going to check it now. Okay, this is what the framing of question. According to that Van 't Hoff equation, non-thermic reaction, that means delta H is equal to 0. Heat neither released nor required. That time equilibrium constant is independent of temperature. Okay, no effect of equilibrium on the temperature. For endothermic reaction, delta H is positive. Therefore, when temperature increases, K, K also increases. This is very, very important word and lovely word. Okay. So these type of sentences you should remember for a long time. Okay. So next importance is on the increase in temperature. On the increase in temperature, you have to, for endothermic, it will be increases equilibrium constant. For exothermic, it will decreases the equilibrium constant. With on the increase of temperature, equilibrium constant will decrease the exothermic reaction. Will decrease the exothermic reaction. Is it understood? So for endothermic directly proportional, for exothermic inversely proportional. I think it is clear now. These two sentences are going to give you 4 marks plus. If you neglect this, you will get -1 mark. Okay, so let us see the next topic. Okay, next topic is units of equilibrium constant. Being a constant, it is not supposed to have any units, but rather it is opposite. Okay, what is that? Kc will have plenty of units, Kp will have plenty of units. Okay, so they don't have units only when delta n, number of moles of product minus number of moles of reactants, are different. Then they are going to have what? Units. Otherwise, no units. Okay. So greater than 0, this is the formula. Less than 0, this is the formula. You can write and practice. Nowadays, these questions are very rare. Okay. So I don't think this type of questions they will ask in near future also. Okay. Next, relation between Kp and Kc. So Kp and Kc. So this is a memory technique, Priyanka Chopra. Okay. P stands for Priyanka, C stands for Chopra, and here it is plus. Okay. PC positive. Otherwise, you can remember it as a personal computer positive. Okay, so because lot of times question are given. Okay, just because of confusion they lost the marks. Okay, Kp is equal to Kc into RT to the power of delta Ng. This is a memory trick. You can use it and you will get definitely plus 4 marks. Okay, so P should come here, C should come here, and here it should be positive. Let them give anything. You convert into this format. If it is, suppose if you keep KP here, KC here, if it is negative, that means it is wrong. Okay. So convert them into this pattern and you can compare. Then delta Ng is equal to number of moles of gaseous product only, number of moles of gaseous reactant only. Why? Because we are using the gaseous equation. Okay. M1 and M2 are product moles, N1 and N2 are reactant moles, and temperature you must and should take Kelvin only. Sometimes when they give fancy number like 100 degrees Celsius, so people are very directly they will substitute, think that they will get the correct answer. No, you should convert into Kelvin, then only you will substitute in this formula. Okay, so this is the formula, memory technique, and precautions you should take and learn from your seniors. Okay, the mistakes made by your seniors or yourself should not be repeated in future. Okay, then we are learning so much of equilibrium constant, but is there any use of it? Yes, definitely. That's why we are studying. Okay. So what is that? Predicting the extent of reaction on the basis of its magnitude. Okay. Suppose A gives A reversible B. and C reversible D. Okay. So here the Kc is equal to 10 to the power of 3. Here Kc is equal to 10 to the power of minus 3. So that means this reaction almost go for the completion. So this is what I told you, extent of reaction. Okay. So magnitude A plus B reaction is almost completed. Okay. And C plus C to D is reaction not at all initiated. And 1,000 parts of the reactants are left over. Only one part is completed as a product. So what do you say, whether it reaction is not at all initiated at all? Okay. Then next is predicting the direction of reaction. So this is very important in the numericals. Okay, predicting direction of reaction. These are simple comparison based, but numericals, this part is very important. Okay. Now let's see the next part. As I told you, predicting the direction of reaction. Okay. Extent of reaction, we can see the magnitude. Higher the positive value of Kc. Okay. Equilibrium constant can never be negative because equilibrium constant is concentration. Can anytime concentration can be negative? No. Pressure can be negative? No. Therefore, equilibrium constant cannot be negative but can be 1 upon something. Okay? Can be 1 upon something, that time 10 to the power of minus possible. Okay? But always Kc and Kp will be positive. Okay? Then uh, direction of extent of reaction we will identify from the magnitude of the Kc value. Direction we will compare with the Qc value. What is Qc? Qc is at any point of time. Okay. At suppose 10 o'clock 32 minutes. You want that reaction will go forward or backward. Okay. So at that point you will measure all concentration, but you are not sure that it is at the equilibrium or not. That time same formula you will use, but you are not sure that equilibrium is attained or not. That time you will use QC. Okay. So at any given point of time, you will find out the concentration of all reactant and product and substitute here. Then you will get QC. And for that particular reaction at that particular temperature, Kc will be fixed. You compare your Qc with the predetermined fixed Kc. If our calculated Qc is greater than Kc, then reaction will proceed in the backward direction so that it can attain the equilibrium. The stable most the stable most state of any reaction is the equilibrium reaction. So everybody wants to stable. So this also wanted to stable. So to get stabilized, it have to attain the Kc. That is, Kc will be attained in the backward direction. If Qc is less than Kc, that means it is yet to reach to the Kc, then it will move in the forward direction. If already Qc is equal to Kc, that means it is need not to worry. It will take rest. Okay. It will not move in any direction. Is it understood? Okay. These are the how you will determine direction of reaction means forward or backward. Okay. Now let's see the next topic. Degree of dissociation, very required for advanced level question. Degree of dissociation formula is very simple, but application is only very difficult. Alpha equal to number of moles of reactant dissociated upon number of moles of reactant present initially. Okay. Now, ammonia, 1 mole of ammonia. It, always remember degree of dissociation is applicable for 1 mole. Sometimes you will think, you will see in the solution X. So that is not for the 1 mole. Alpha, if you are writing, that should be 1 mole. But you can make it for more than 1 mole by multiplying that with the uh, correct value. Okay. Suppose if it is for 3 moles, then 3 into 1 minus alpha. Okay. So here this writing of this equation format is very important. So try to practice for more and more questions. There is no fixed formulas for this. This will keep on changes as per the reaction, as per the reaction stoichiometry. Out of the A moles initially 0 and 0. Okay. So there is a change 1 minus alpha. If from 1 mole alpha is dissociated, from A moles A into 1 minus alpha will be dissociated, and for 1 mole half mole will be formed. So for A moles will be A into alpha by 2 and 3 into alpha by 2, A into alpha by 2. Okay. So this writing you should practice for the different type of reaction, how it is minus, how it is plus, and what is the final equilibrium constants. Okay. This type of practice required for numerical solving in terms of the degree of dissociation. Okay, I think you all will do that so that you will not have any problem in the solutions. Okay, now let's see the next calculation of Kc. Okay, calculation of Kc. There was a previous question, integer type question converted by using the two normal questions. Okay, so this is A moles. In the previous example, we have taken one reactant producing two products. Here we are taking the reciprocal of that. Two reactants are producing one product. So A moles, B moles gives 0 moles. So A minus X and B minus X. Here this coefficient plays a vital role here. Okay. And X moles are consumed and X moles will be produced. So very important information. People forget to divide with the volume, thinking that that will not affect. Okay, I agree. Volume will not affect in the calculation in the two condition. Okay, what is the two condition? First of all, number of moles of reactant must be number of moles of product. Okay, that is the one condition. Volume you need not to worry. Okay, otherwise volume is given as 1 liter. Okay, but 90% happening in these two cases. 10% people are losing the marks, forgetting to when they give 2 liter. Okay, here you can use this. You need not to use this formula because number of moles of reactant are 1 plus 1, product also 2. Okay, therefore there is no worry about dividing with V or not dividing with V. Also don't affect your calculation. But if you divide, if you don't forget to divide when volume is given 3 liter, 5 liter, and number of moles of reactant and products are not equal, that is going to give you a wrong answer. Okay. Unintentionally, you may make mistake. Now let's see the next step of the same derivation. Derivation is same, but next step. So finally, we will get Kc is equal to product upon reactant. Here, the main word you will remember, okay? Because it was long back in the advanced. So this time it may repeat. Which word you will remember? 4. Okay. This 4 you will remember because that time advanced was having integer and mains was not having integer. So as now it is introduced in the mains also. So this may be copied and pasted with the reaction change, but concept will be same. Okay. So when one type of product with 2 moles are there, this 2 will be there. Now I will take the successive example where 2 products are there, 1 mole each. That time it is not going to affect. Okay. Let's see what is that. Here you make a mark over here in your notes also. This 4 came because one type of product 2 moles. Okay. So if 2 products of 1 moles, what is the result? Okay, that we'll see in the next example. See the next example, two products but one mole in the same derivation. Pattern of derivation is same. Okay, same 1 minus x divided by volume Kc is equal to concentration of PCl3 into concentration of Cl2 divided by concentration of PCl5. But after simplification, you will be surprised to see one value is missing. What is that value missing? If you know it already, then you are in a good condition. If you don't know, that means you have to learn. What is the value missing here? What is the value missing here in the previous formula? Okay, this is the value missing. That time what they have done, that value divided by this value. Okay, so the integer answer was 4. Okay, why I am specifically telling, if I say something specially means lot of chances of examination question. Okay, so if it is of 3 moles, then it will be 3 cube. Okay, so like that they may change the value or change the equation, but you are perfect in the deriving the formula, then no problem of changing the question with values. Okay, so let us see the next question. Next topic, multiple equilibrium. I told you we are going to study three important topics. What is that? Multiple equilibrium, and second one is, what is the second one? Okay, that you will see it now. Multiple equilibrium. See, this is one equilibrium. Okay, and one of the part of this already I have sometimes I have explained in the derivation of equilibrium constant for the multiplied equation. Suppose this is one equilibrium. For this is Kc1. This is another equilibrium. For this Kc2. So when I add these two, C and C will get cancelled. E will not get cancelled. Okay. A, B and E are the reactant, and F, G and D are the product. Okay. So when two equilibrium equations are added, their equilibrium constant will be multiplied. When you multiply these two, this C will get cancelled. Final answer will be this one. Okay. Final answer will be this one. FG. Actually, it is D. Actually, here it is D. Okay. So DFG divided by ABE. Is it clear now? This is overall reaction for the multiple equilibrium. Multiple equilibrium. Now let's see the next type of advanced topic and most important topic, problem solving techniques. I will tell you. Okay, so this is the derivation, Kc1 into Kc2 is equal to Kc3. Okay, what is that important value I told you? Yes, that is simultaneous equilibrium. What is simultaneous equilibrium? See, CaCO3 decomposing to give CaO plus CO2. And here CO2 is a gaseous product, but it react with one more other reactant to form another product D. Okay, that is CO. So both are existing together. That is the difference between multiple equilibrium and simultaneous. Multiple means one will occur after the other. Sequential. First reaction will complete, then the second reaction will take place. By the time second reaction is taking place, first reaction won't exist. That is called as a multiple equilibrium. But here it is not so. During the second reaction also, at that point of time, first reaction also will takes place. That is called as a simultaneous equilibrium. I think it is clear to you what is the difference between simultaneous equilibrium and uh, multiple equilibrium. Multiple equilibrium you can multiply, but here you cannot multiply because all are together. So for that only this numerical solving technique. Here you will take a minus x. Here it will be x. This CO2 won't be x here. Okay. So one of the student previous examination done mistake. Why this is not x, sir? Because at the same time, simultaneous means at the same time. This is also consumed in the next reaction. See, simultaneous means here also x minus 5, here also x minus y. Okay. So that value you have to be very careful. That's why this type of questions you will find in the advanced level or aims level. Okay. Next, let I think you will keep a star mark on this in your notes so that when you open your notes immediately you are you should be able to strike into it should be able to strike into your mind. Okay, you should be able to see this immediately. Okay, simultaneous equilibrium. Next, let us see the calculation of degree of dissociation. This is also very important. Vapor density. Okay. So first I am taking 1 mole. Okay. If it is not unitary mole, what you have to do? Just small modification. Okay. PCl5 1 minus alpha, alpha and alpha. Suppose if it is 2 here, what you will do? 2 alpha. But 2 is not there. Here also 2 will not be there. So total number of moles at equilibrium 1 minus alpha plus alpha plus alpha. So this and this will get cancelled. This will be 1 plus alpha. Total number of moles at equilibrium. Then you will calculate equilibrium constant by substituting these. By substituting these. Okay. Okay, this is the calculation of degree of dissociation. First step. This is a derivation and it is applicable only for the PCl5. So it can be used for other by similar modifications in the derivation. Okay. So V is the volume occupied. Now we can say that volume is always inversely proportional to density. Or density is inversely proportional to volume because density is equal to mass upon volume. But why we are not considering the mass here? Because mass is conserved during the reaction. Reactant mass is equal to product mass. So but volume may increase or decrease changing the number of moles. Okay. So once moles will increase, volume will increase, then it will decrease in the density. Why I am worried about the density in this? Because vapor density, our aim is to calculate the vapor density. Okay. So density or vapor density inversely proportional to volume. Okay. Or we can say, see, initially only one mole PCl5 was there. So D is inversely proportional to 1 by V. But after dissociation, 1 mole have given how many moles? 1 plus alpha. If 1 mole volume is V, 1 plus alpha will be 1 plus alpha into V. Okay. So this is how small d is at equilibrium or after dissociation. Capital D is before dissociation or pure PCl5. Okay. So after substituting and simplifying, we get alpha is equal to capital D minus small d divided by small d. So don't forget capital D is very good. Density initially, small d is density of equilibrium mixture. Density of equilibrium mixture. Now, because why I am specifying this, sometimes they may see in some books, if you refer by mistake, DT, theoretical they will write. Theoretical means initial. Okay. And DE. So E means experimental or at equilibrium. So if you by mistake, if you study from the other books, you should not confuse the terminology in the book used and formula I've given is same, but terminology will be different. Okay. So this is for 1 mole. Okay, 1 mole. But it is not that always we will be having the question with 1 mole only. If it is more than 1 mole or if it is in terms of the molar mass, molecular mass, then how to deal such questions. The next slide will give you the answer. Okay. So as we know that vapor density, 2 into vapor density is equal to molecular mass. So here you will find this empty theoretical molecular mass and at equilibrium. Observed molecular mass means at equilibrium. Okay. So alpha formula again and again I am repeating, this is only when number of moles we have taken initially 1 mole. If they are more than 1 mole, one slight modification. I will check your observation in the next slide. I will ask you what is the change in the previous formula and this formula. Okay, tell me the what is the difference between previous formula and this formula. Okay, in the previous formula, what is the difference? 1 upon n minus 1 was not there. Okay, so once you know the differences, you already remember the formula. Okay, so this is about the when n moles are dissociated 1 upon n minus 1. N moles are dissociated means 1 mole of reactant only. Okay, it is giving n moles of product. Okay, and in the previous batch, some student asked, sir, when n is less than 1, how degree of dissociation can be negative, sir? Anybody of this batch can answer? Okay. So degree of dissociation means one mole is dissociating into more mole. So n can never be less than 1 or n can never be equal to 1 provided it is dissociation. Dissociation means one mole breaking into 1.5 also okay, 2 moles also okay. So that you will never get such situation. Is that understood? So let us see the next slide. So next, already we have studied this in the thermodynamics. That time also I told you this is equilibrium and thermodynamics combined formula. Okay. So delta G is equal to, there we have studied without equilibrium also. Okay. Delta G is equal to delta G naught minus, okay, RT. Here this formula is applicable only for the equilibrium condition. Non-equilibrium condition, go back to thermodynamics, revise that formula. Okay. And K can be either Kc or Kp. Okay. Delta G naught depends only on RT, as temperature will be in Kelvin. If R value will take it as 8.314, delta G units will be in joules. R value if you take it as 2, delta G naught will be in calories. R value people are confused after studying in 3 chapters: states of matter, thermodynamics, and equilibrium. Sometimes we will study in electrochemistry also. Be perfect in using the R values properly. For what units R values are required. Okay. What R value you have to substitute. Okay. So many times in my previous lectures also revise that. Lee-Chatler principle. What is the next topic? Lee-Chatler principle, one of the most important theoretical direct based question. Okay. When was it was direct based question? Some 4 to 5 years back. Okay. Now this Lee-Chatler principle is combined with, Lee-Chatler principle is nowadays combined with the numericals. So you will only come to know once numericals are perfect and Lee-Chatler concept is perfect. Okay. So chemical equilibrium, present balance between. The main thing is here, in most cases, this balance is quite delicate. Okay. And change in concentration, change in pressure, change in volume, change in temperature may disturb balance. Okay. So it happens with your life also. Some problems will be there. It will disturb you, but you should be like equilibrium. For time being, you may be disturbed, but after that you should bounce back. You should be stabilized by attaining the equilibrium. That is what Lee-Chatler principle says. Okay. Shift to the equilibrium position so that less of the desired product is formed. Okay. Suppose in some situation you are disturbed, you will do in such a way that the disturbance will be nullified. Okay. So nullified it is sometimes in the previous, I think 2013, partially offset word is used. So that time people were not able to understand the meaning and not answered. Partially offset means it is going away from that disturbance. Okay. So according to Lee-Chatler principle, every reaction wanted to stay in the stable equilibrium, but there are some disturbances by application of some stress. Stress will be concentration, pressure, volume, temperature change. So even though you apply stress, but it will retain back after some time. After it will take some time, but the time taking will depend on the type of reactant and product. It will bounce back to the equilibrium back. Okay. So this is what the Lee-Chatler principle says. Okay. Next, here Lee-Chatler principle, I told you what are the effects? Concentration. First thing is the concentration. First thing is concentration. Okay. So concentration, what we can do? We can increase or decrease. We can increase or we can decrease the concentration. Okay, so we can increase concentration of what reactant, we can increase, or we can increase the concentration of product. Okay, same way we can decrease the concentration of reactant, or we can decrease the concentration of product. Okay, so that time how the equilibrium is able to manage, how the equilibrium is able to manage. Okay, so if the concentration of reactant increased, then equilibrium will shift in the forward direction. In which direction? Forward direction. If concentration of reactant increased, equilibrium will shift in the forward direction. If you increase the concentration of product, then it will go in the backward direction. It will go in the what? Backward direction. And here it will be backward direction. Okay, and here it will be forward direction. Okay, like this you have to remember the Lee Chatler principle application. First application is measuring direction of movement of the equilibrium once concentration is changed. What is changed? Concentration is changed. Okay, next, after concentration, temperature already we have studied. What is the temperature we have studied? If it is endothermic or exothermic, what is that principle? Van 't Hoff equation. Okay, so for uh, endothermic equation, okay, and actually there is no particular equation in only endothermic, only exothermic. Okay, so endothermic in the forward means exothermic in the backward. So I will take endothermic in the forward. Okay. If the reaction is endothermic in the forward, then temperature is increased. Equilibrium will shift in the forward direction. High temperature is favorable. Remember only two sentences. High temperature favorable for endothermic reaction. Low temperature favorable for exothermic reaction. Okay, you can write it somewhere else and you can practice it afterwards. Okay, whichever direction is endothermic, in that direction equilibrium will shift when temperature is increased. When temperature is what? Increased. I think it is clear now. Okay, now let's see about the pressure condition. What is the other condition? Pressure condition. Okay, so pressure will be effect will not be there when delta Ng product moles of gaseous or number of gaseous moles of reactant are same, then there is no effect on the equilibrium. Okay, few days back, sorry, not few days, few years back, there used to be question in which of the following pressure effect will not be there. Okay, so but I don't think that much fortune you are that easy questions will be in your session. Okay, so, but you will calculate in that condition. What you will do? You will calculate the delta Ng. So, if delta Ng is 0, okay, number of moles of gaseous product is equal to number of moles of reactant, then you increase the pressure or decrease the pressure, there won't be any shift in the equilibrium. But let us take number of moles of product in the gaseous state is greater than number of moles of reactant in gaseous state. Okay, so always when pressure is increased, then equilibrium will shift in the less number of moles side. Which number of moles side? Less number of moles side. Here reactant sides are moles less. Okay, so that means it will go in the backward direction. Okay, this is the thumb rule you will utilize. More pressure, less moles. Less pressure, more moles. Okay, so accordingly you can apply it. Is it understood? So this is about the pressure. Then what about the catalyst? Okay, so catalyst also we have studied. Inert gas also we have studied. Catalyst will not affect the direction of equilibrium. Okay, because it will have same influence. It will have same influence in the forward direction and backward direction equally. Therefore, it will not shift the equilibrium in either direction. Okay, here if the inert gas is added, okay, inert gas added, one sentence I will tell you. If you remember that, then you need not to learn something new. It is old value based only, but new way of asking. Okay, inert gas added, inert gas added, but at constant pressure. Okay, so to keep pressure constant, what should happen? Volume must increase, volume must increase. Okay, so therefore the same effect produced by increase in volume. Okay, so constant pressure, that means volume increases. When inert gas is added, volume increases. Whatever the effect we have studied in increase in volume, increase in volume means decrease in pressure only. So decrease in pressure, both are same. When pressure is decreased or increased in volume, what will happen? Equilibrium will shift in the, equilibrium will shift in the more number of mole side. Okay, more number of mole side. Same way, inert gas added at constant volume. Constant volume means number of moles will be same. Volume is constant, so concentration is constant. Therefore, equilibrium constant will not change. Okay, at constant volume, no effect. Whereas inert gas is added at constant pressure, will increase in volume. Okay, so it is similar to, not exactly equal. It is similar to increase in volume means decrease in pressure. Okay, so either you can use this sentence, volume increased. So this is about the addition of inert gas. Okay.